Hello everyone. Today we are going to discuss about the RLC circuit, right? So, uh, first of all, before getting into the RLC circuit, let us see how a AC circuit behaves on a purely resistive circuit, on a purely resistive element. So now this is the resistive element incorporated in an AC circuit. Now the supply is given by Vm sine omega t, right? Or we can write V equals to Vm sine omega t. Now, for a purely resistive circuit, we have already gone through this. We have already known that there is no change or there is no angular difference between the current and voltage in case of a purely resistive circuit. So, the phasor representation of a purely resistive circuit looks like this. Now, the phasor representation of a purely resistive circuit, in this phasor diagram, we can see that this vector is representing the voltage V, right? And the IR vector, which is representing the current through the circuit. Let's say this one is IR, right? So we can see that IR is overlaying with the vector of the voltage. There is no angular difference between. So we can say that current remains in phase with the voltage in a purely resistive circuit. Now, coming to the circuit which is purely inductive in nature or inductive element incorporated within a AC circuit. Now, in this inductive circuit, we can say this is also the voltage source V, which is represented as Vm sin omega t, and this is the resistive element L, right? So here this is wrong. We can say although we are representing it as voltage, so this is wrong. We can say this is VL, or the voltage drop across the inducted L, right? So we can here see that the inductor is the voltage inside the inductor, or the voltage drop across the inductor is leading the actual circuit voltage by an angle of 90 degrees. So here the phase difference or the phase angle is 90 degrees. Now from here we can say that current will lead the voltage by 90 degrees in case of a purely not resistive, this is inductive circuit. Inductive circuit. Now coming to the third diagram where it is a purely capacitive circuit, or only a capacitive element is incorporated within the circuit. Here also the AC supply voltage is Vm sin omega t, and there is a capacitance which is represented by this, and the voltage drop across the capacitance is Vc, right? So here also it will be Vc. Now here we can see that the voltage phasor or the voltage drop phasor across the capacitance is lagging the supply voltage by an angle of 90 degrees. So we can say that the current will lag the voltage by 90 degrees in case of purely capacitive circuit. Right? Now from here we can say that resistance does not include any phase difference between voltage and current, or supply voltage and current. An inductive element incorporates a lagging voltage or lagging current when applied to a purely inductive circuit, and the capacitive element makes the current lag by 90 degrees. Now, let's see if we place an inductive element in a purely resistive circuit. So the resistive circuit has a series inductance with it. Now here, from using KVL, we can write that the supply voltage is incorporated with two drops, that is the voltage drop across the resistance and the voltage drop across the inductance. So V equals to VR plus VL. From here we can write this VR as I into R, where I is the supply current, that multiplied by the resistance, and the voltage drop across the inductance, which is I multiplied by j omega L, right? So now after this we come to this phasor diagram. Now this IR and VR, this is all known to you, right? From the previous slide you can see that IR for a purely resistive circuit lies over this VR or V, or the supply voltage, right? Now again, for the inductive element, the voltage is leading by 90 degrees. Now there are two VRs, two V's. One is VR and one is VL, which is acting due to this inductive and resistive element of the circuit. So we have to take the resultant of these two vectors to see where the actual voltage is acting. So if this is VL, we can place this VL over here. So now this is the new VL and this is VR. So the actual voltage that is acting over here is V. So we will be using this. We will be using this in a while, but before that we have to find the impedance of the circuit. So impedance, where V equals to I R plus j omega L, taking common I, where I is common in both the cases as the series circuit. So this I will be going through this resistive element as well as the inductive element. Now we can say, we know that Z equals to V by I, which means this I comes underneath this V and the impedance becomes R plus j omega L. Now to find the magnitude of this impedance, what we have to do, we have to find the magnitude of this Z, which is root over of R square plus omega L square, and the angle between them is tan inverse of omega L by R, right? So now the voltage equation will be the same, which is Vm sine of omega t, and the current equation will become phi lagging to that of the actual supply current, where actual supply current is Im of sine omega t. So the current is leading by an angle of theta, and this is the signal representation um, of this circuit, where V is represented by this red sinusoidal wave and I is represented by this yellow sinusoidal wave, where the angle difference is theta between them. Now next we will be seeing if a capacitive element is incorporated within a purely resistive circuit. So this is quite similar to the previous one, where we can say that applying KVL V equals to VR plus VC, and VR is represented as IR, and VC is represented by as I into 1 by j omega c. Now here we can see that VC, we have seen from the first slide that VC is lagging in nature. It lags the actual voltage by an angle of 90 degrees. So VC is acting 90 degrees to the actual supply voltage. And if we place this VC over here, this is VC and this is VR. If we place this over here, we will get a resultant vector which represents the actual voltage to the circuit, right? So this to find the impedance again, we have to find V equals to I uh, R plus j omega R plus 1 by j omega c, which gives Z equals to R plus 1 by j omega c, and then we can find the magnitude and the angle or angular difference between these two waveforms, where Vm equals to V equals to Vm sine of omega t, and I equals to I sine of omega t plus 90 or plus theta. Sorry, it's not 90, plus theta, because it is lagging in nature. So this is the waveform for the for purely sorry for a series RC circuit. So that's all for now. We will be talking about the RLC circuit or series RLC circuit in our next video lecture. Until then, stay safe, study from home, and do it. Thank you.